Thank you very much to everybody for coming. I'm going to start off and then I'm going to turn it over to Dr. Plotkin to talk a little bit about his research. But I thought I would talk a little bit about the incipient trial that you all have heard about over the last few years that we've been really working on this trial. But first, let me start by thanking Bill Park and the whole Park family for continuing to support our research and continuing to invite us out here every year. It really is one of the highlights of my year because you all are a great audience and you ask wonderful questions. So please continue to ask questions and stay involved. So I start with this slide most years just to remind us about the landscape of where brain tumors are in cancer. We're a pretty small cancer in the landscape of cancers. There are only about 24,000 brain tumors each year in the United States. But unfortunately, we count for about 3% of all deaths. So we're a pretty malignant type of cancer. So clearly we have our work cut out for us in order to improve the care of our patients. And when you look at the breakdown of brain cancer, glioblastoma makes up the largest part of this pie, and it's also the most malignant type of primary brain tumor. So that's why we really focus, a lot of my research is focused on this glioblastoma and trying to figure out better ways of fighting it. Now, one of the challenges we face in glioblastoma is that this is a really smart tumor in that it shuts down the immune system and prevents the immune system from attacking the tumor. And it does this through several mechanisms. One of them is that there's this dearth of professional antigen presenting cells. So these are cells that are supposed to present to the immune system the tumor components that are foreign. And those don't exist in glioblastoma tumor microenvironment. We also see in glioblastoma that immune effector cells, those cells that are important for turning on the immune system, don't make it to the brain. They stay in the bone marrow. And we also know that temozolomide, which is the chemotherapy we use most for glioblastoma, as well as steroids, which we use to dampen down the peritumoral edema, the swelling that we see in the brain, those also have a profound effect on white blood cells, which again are the activating, fighting cells of the immune system. So those get shut down in glioblastoma as well. And then, as I said, the tumor is very smart. It secretes all of these molecules that really turn off the immune system within that tumor microenvironment, so it cannot wake up and fight the tumor. So CAR T therapy is one approach we hope to use to overcome that immune tolerance. And so the way CAR T therapy works is we collect from the patient their own white blood cells. We send it off to the lab to genetically modify it by inserting these genes into it so that the genes make the cell express certain antigen receptors that the tumor expresses so it can target the particular tumor. And then we expand those cells and then we reinfuse them and inject them back into the patient so that then the cells in the patient can go target the tumor itself. And so the trial that we're doing is really based on work out of Dr. Brian Choi's lab, and he came here a few years ago. So you heard a little bit about this already, but really the novel thing that his science did is that his CAR T therapy targets two antigens, both this EGFR V3 antigen as well as this EGFR antigen. The specific antigens are less important, but just know that it targets these two antigens, but it also can turn on that local immune response by signaling through this T cell receptor, which is an important component of the immune system, to help activate it and turn on the immune response. And so that has led to our slightly cumbersome name trial, the incipient trial, which we have started. So this is a non-randomized open-label phase 1 study. We're enrolling up to 21 patients, and we have several arms that are enrolling. We've completed the safety run-in, and then we're currently enrolled into an arm with recurrent glioblastoma with both these two target antigens, as well as a recurrent glioblastoma arm with just one of the two target antigens, because we think that our CAR T is effective against both, which is a positive because it means it opens up the study to a larger population of patients. And eventually we're going to open an arm to patients at initial diagnosis where they first discover that they have a glioblastoma. And so this was the the schema of how we treated those first patients. They go through that leukapheresis process where we take out their T cells and it gets sent to the lab to be engineered to target the tumor. And then patients have to go through surgery, at which time a special catheter is placed into the brain through which we can then inject the T cells. And then they got the T cells injected into that special catheter and then were followed for response to treatment. And so we are very excited because, as a lot of you have mentioned tonight, the results of this first safety run-in cohort was published in the New England Journal last early spring. And these are sort of the patient characteristics of our patients. And the main point of this slide is just that they are typical, representative of recurrent glioblastoma patients. And what got us so excited is that we really saw this dramatic and rapid response in all 3 of our patients after just a single dose of our CAR T infusion. So you can see here these MRI scans, and so you see this contrast enhancement that really went away quite rapidly over time, and that happened in all 3 of our patients. And this doesn't happen in any other treatment for GBM other than vascular targeting agents like Avastin, which you'll hear about in a little bit. So this is clearly having some impact on the tumor itself. And what was also exciting is because we had that special catheter going into the fluid-filled spaces that we all have in the brain, we were able to measure our target antigens. And so what we found is that there was an initial increase that we could measure in the CSF, or cerebrospinal fluid, that was really representative likely of tumor cells dying off and releasing their contents into the fluid for us to measure. And then that measurement of the antigens went down over time, really suggesting that we were having an on-target impact with our therapy. We also were able to determine that the treatment was safe, and we had very little toxicity, and the toxicity was manageable. This just shows you that we had 3 different ways of measuring tumor toxicity and really had very low-grade manageable toxicity in all of the patients. What we did learn from this study, looking at pharmacokinetics, is that we were not seeing persistence of our T cells. So when we looked in the CSF, in that fluid, we saw that the T cells were decreasing by day 28. And the inflammatory cytokines, those inflammatory markers that suggest that the immune system is turned on, were also decreasing by day 28. So there was a drop-off in how long the T cells were continuing to circulate in our patients. What was good, though, is that when we looked in blood, we really only saw transient detection of the T cells in the peripheral blood, which was good because we really want the T cells to stay in the brain and not leak out into the blood circulation. So in summary, in our 3 patients, we really saw this remarkable early decrease in contrast enhancement, suggesting some response within the tumor itself. We had very manageable toxicity, and we had evidence of on-target effect of our T cell therapy. And so, unfortunately, 2 of the patients did experience disease progression. One patient had a later progression, is still doing very, very well on second-line therapy. And so we've learned a lot from this trial, and we've modified it now to figure out ways to enhance that T cell persistence. So that's what we're doing now, is we're sort of modifying the protocol, and we're seeing with those initial results that we are seeing a little bit more persistence of the T cells. So a lot of work, a lot of excitement, and we're making incremental progress towards optimizing this therapy for these patients. And so, just a thank you to all of you for really supporting the work and helping us to move this along. And hopefully, if you invite me back next year, I'll have more updates on how we've tweaked the protocol and are really helping to help these patients who are really desperate for better treatments.
Well, this is my first time to join you here, so thank you very much for this opportunity. And thank you to Bill and the entire family for all the support over the many years. It's very hard to bring things from our clinics into reality. I think everyone knows that, and there's no question that philanthropy from families is just a critical part of what we do. And so thank you for that. I'm going to tell you a slightly different story, but a story that's, I hope, as exciting as that, and that is to tell you about a genetic syndrome called NF2-related schwannomatosis and the impact that MGH has had worldwide on the care of these individuals. So NF2-related schwannomatosis is a condition that you're born with. You're born with it if you have a genetic variant. We used to call these mutations, a mutation in a gene called the NF2 gene, and if you're born with that, you are predisposed to develop tumors. And you're probably familiar with something, a similar condition, distinct but similar, of hereditary breast and ovarian cancer, like BRCA1 and BRCA2. Same idea. You're born with a genetic variant, and your risk of having tumors is high. So I take care of multi-generational families from the Boston community and really worldwide who come to Boston for care. Now, one thing I should have put in here, but I didn't, is to say that the NF2 gene was cloned or identified at Mass General Hospital in 1993. This is before the Human Genome Project. This is when they were doing something called positional cloning with Jim Gissell and Bob Martuzza. These are people who are still active at MGH. So we have a very long and powerful history of working with families affected by this condition to improve care. It's rare. About 1 in 63,000 individuals if you look in the United Kingdom. And these people develop tumors, multiple different tumor types you can see on the right. In the top left MRI scan, you see a person. The arrows show you benign schwannomas, benign tumors of the nerve sheath, which occur on the hearing and balance nerves. On the right, you can see the arrow showing you a meningioma inside the brain. Here, on an MRI scan of the spine, so this is the brain, this is the spine, you see a spinal tumor called an ependymoma. And finally, in this bottom right, you can see multiple tumors that affect the spine called schwannomas also. So these are spinal schwannomas. So these are individuals who are predisposed to get tumors, multiple types of tumors, and within a tumor type, multiple tumors. So you can imagine the complexity and some of the situations that people ultimately end up in with multiple tumors. So most of our patients, 80%, present as adults, and they present with symptoms related to the tumors in the hearing nerve. So they present with hearing loss, tinnitus, which is ringing in your ears, or vestibular dysfunction, balance dysfunction. Children, which represent about 20% of the people who come to my clinic, actually don't get those tumors till later in life. They present with other manifestations like eye problems or seizures or other things. And even though all 4 types of tumors I've shown you here are histologically benign, meaning you look under the microscope, there's no cancer, because there's so many, because they're bilateral, unfortunately they have terrible, terrible morbidity, and the clinical course for patients is very challenging. And so I'm going to tell you a story about developing this drug bevacizumab, also known as Avastin, for vestibular schwannomas, which are those benign schwannomas that develop on the hearing and balance nerves. And what's unique about this condition, if you look at vestibular schwannomas in general, very common. 7% of all brain tumors are these tumors that affect, benign tumors that affect the ear. What's unique about this genetic syndrome is they happen on both sides, bilateral. And what that means is you go deaf at a time when it's very hard to learn a new language. So when people say, why don't you learn sign language when you're deaf at 24? The answer is it's like learning German or Chinese. And so these people end up being what we call late deafened. Very, very challenging, as well as having other situations. When we look at natural history studies, we know that things can progress pretty quickly once you're diagnosed. About 40 months you start losing hearing. Tumors start growing within 14 months of diagnosis. And part of the challenge is the tumor size and the hearing function are not well correlated, so very hard to predict what's going on. And so what's the standard of care? What have we done for many, many years? Well, surgery and radiation are the mainstays of everything we do. And without going to the details here, because I don't think it's that important, I'll just tell you that because there are multiple tumors, because of this genetic syndrome, outcomes for people after surgery and after radiation are not very good. And in fact, the most common reason people get either a paralyzed face or lose hearing is from the surgery that saves their life because they have brain compression, but unfortunately they come out of it with hearing loss, if it's both sides, complete deafness, and facial weakness. So a really challenging, horrible, horrible condition in some ways. So if you've lived in Boston for 20 years now, you will remember Judah Folkman, maybe, who's one of our pioneers who worked at Children's Hospital in Boston and really should have won the Nobel Prize for his pioneering work on angiogenesis, which is the study of abnormal blood vessels that develop in tumors. And there's no question, while there was a lot of hype about how effective targeting angiogenesis will be, and I'll tell you what it is in 1 second, we know that we didn't achieve curing cancer, which was on the cover of Time magazine, but it's still critically important. So if you look here on the left, you see a cartoon of a normal blood vessels, where you have the arteries, which are big, then the arterioles, which are small, then you have the capillaries, which are very fine. That's the oxygenated blood, the red ones here. And then you have the blue system here, which are the veins. The small capillaries go to the veins and go to the venules and goes back to the heart. And what you see is this beautifully regulated vascular bed, we call it, when you have balance of proangiogenic, so they create blood vessels, and anti-angiogenic. They're in perfect balance. The problem is for tumors, they disrupt that balance, and so we get very abnormal blood vessels. And this has been one of the hallmarks of cancer, and one of the things that causes lots of difficulty, because when you have bad vasculature, you can't get chemotherapy there, you can't get radiation to certain parts of the tumor. And so correcting this abnormal vasculature has been very important or interesting. So the first thing we did, because angiogenesis has been a big part of Boston research for really decades, we went and decided at Mass General Hospital to look at the blood vessels in our vestibular schwannomas. And that was kind of new at the time, believe it or not, because we all thought benign tumors would really look like normal tissues. They wouldn't look like cancers. But in fact, what we discovered is that these blood vessels were abnormal in really a very similar way that we saw with cancer. And so it led us to look to this drug, bevacizumab or Avastin, which is approved in the FDA for many, many indications of cancer. It was available to us at MGH, had a very good safety record overall, but was scary because it was for cancer. And so it took some very brave patients to be willing to try this medicine because they didn't have any more good surgical or radiation options. And so I always talk about my first two patients. Patient one was about a 14-year-old boy from Cape Cod who had just gone on hospice. And I'm quite literal when I say within 1 month he was jet skiing on Cape Cod afterwards. So it was really a dramatic effect. And patient two is shown right here. And I want to show you this graph because it's so remarkable. We tracked her hearing for many years. You see a scale here from 0 to 100. This is perfect hearing up here, and this is no hearing, and this is time in months. And here's where we gave her Avastin. So if you look before we gave her Avastin, you could see that hearing was dropping in her only good hearing year. And really, she was deafened for about 6 months beforehand. We gave her Avastin, and you can just see this really miraculous return of hearing. And here's an example, not her, but somebody else, of the tumor shrinking. And you can see they don't go away. This is not a cure, unfortunately, but we do see shrinkage. And when we looked at this data, you can see here about a little over 50% of people's hearing improved, the tumor shrank. It really was pretty much a home run, at least for our first new medicine. And so this was published also in the New England Journal back in 2009, but it was a series of patients who really last-ditch effort. It wasn't a clinical trial. It was really a way to help them, so we really had to think about more. And just to show you before I tell you about the next trial, here's an example that even though most of the time the tumors don't shrink much, here's a really remarkable response. If you look at the yellow arrow, you can see this very large cystic lesion. You can see the dark spot is the cyst in the middle, who came into MGH and basically said, I'm not having surgery. She couldn't walk anymore, so this was her last-ditch effort. And now she pops in and out of Boston from the Cape also because she's feeling pretty much normal. I would say the last thing that we learned is really a testament to MGH radiology and science is Elizabeth's old boss, Greg Sorensen, believe it or not, helped us try to unravel why was the medicine helping people. And what his lab did at the time was to look at the leakiness of blood vessels. Elizabeth had referred to the leakiness of blood vessels being one of the primary problems. And you can see through color coding here over time that leakiness dropped with bevacizumab. And so what we came to understand from these studies is that what we were doing was really taking the swelling away from the nerve, and by doing so, we could shrink the tumor and we could also restore hearing because the nerve could now fire normally. So how to move forward? The first thing as we did is we partnered with Johns Hopkins Hospital, one of my close colleagues there, as well as the National Cancer Institute, and we did the very first phase 2 trial. So this is a trial that moves forward in time. It's controlled, it's monitored by the FDA. And the first thing we did is we said we're going to treat people for 12 months and then we're going to stop. Let's see how long we have to treat them. So we got similar results with about 40% of people having improved hearing, about 40% of people had their tumor shrink, very few people had tumor growth, so at least they stayed stable. And so that really confirmed that initial work that we did at MGH. The next thing that was incredibly important is when we stopped the drug, we learned that the tumor started growing again after 6 months. So unfortunately, this reversal of the swelling was not permanent, and we knew that we had to figure out how can we treat people long term with this drug, because most people are in their 20s when they need treatment. So this led to a second trial, or a third study, where we now expanded beyond the 3 sites. This is now a national trial across the United States through a consortium sponsored by the Department of Defense, God bless the DoD, where they sponsor 17 or 18 hospitals to cooperate to do these trials. And we asked this question. The question was, number one, can we do better if we give more medicine? I had initially given people medicine at half dose, half the cancer dose, because I said it's not cancer, why do that? So we went back to the drawing board. We said, well, what if we do give people cancer doses? Let's do that for 6 months and see how we do. And then let's lower the dose because we know we can't treat somebody forever. So we're going to do low dose maintenance therapy. So how can we improve tolerability? And that's these 2 phases, what we call the induction phase as well as the maintenance phase. And to make a long story short, we did not see a benefit with induction therapy. That is, when we did high doses, we didn't see better outcomes than we saw at regular doses, which was a really important finding. What was in some ways more interesting and more important is when we went to very low doses, we also were able to maintain benefit. And so that was really important, and now we're learning, have learned and continue to learn, how do we treat somebody for 10 and 15 years? And believe it or not, we're looking great now at our data at Mass General. We have the longest history of treatment for patients, and we're now pulling that together for a manuscript. The other point I'll make here is we did learn, unfortunately, that children benefit less than adults. And that's just the way it is. We don't fully understand why. So we are really all out to try to help the children affected by NF2 and have, it's a different talk, but a lot of work trying to see how to help our young patients. So finally, where do we go from there? I told you about the US. We went from MGH to the US. Well, of course, my colleagues in the United Kingdom, they have a wonderful national health service. They took it up a couple years after us. They didn't do it on a clinical trial, they did it as part of their National Health Service. And so what you can see here in the pink is that essentially they had the same results we did. That really what we call real world evidence confirmed what we saw in clinical trials. And most recently, the Japanese physicians have been studying this in Japan and also getting very similar responses. So it really has now shown to be effective around the world. And so this is the last slide, because I know I'm heading up on time, is just to say, what have we learned from the series of trials that began Thanksgiving 2007? I would say right around this time, 2007, because I talk about all the time with the patients who are still getting medicine. It does improve hearing, which is just something that we had never seen before. Usually when you lose neurological function, you don't gain it back. Bevacizumab, we did have to give it chronically. And that we could divide this into an induction phase that would get people to have improved hearing and stop the tumor from growing, and then a maintenance phase where we give low doses. And of course, as I mentioned, that pediatric patients don't do as well. So where are we in 2024? We've just, we're about to ask a drug company to allow us to give bevacizumab plus some of the immune therapies that Elizabeth has been talking about, to give them together to see if we can boost some of this anti-angiogenesis with an immune therapy effect. And we're hoping that we'll be able to move that forward. So I'll just stop there. And we have a large team at MGH and around the country that have helped us, and it's been very satisfying to see MGH from 1993 with the cloning of the gene to really moving forward some of these therapies. So happy to answer questions with Elizabeth after.
What about the CRISPR technology? Is that in any way being studied to see if that could
That's for me,
possibly,
right?
yeah,
Yeah.
NF2, right?
NF2 related schwannomatosis and the diseases I take care of are the best diseases to go after with gene therapy, because they're single gene disorders. So unlike many cancers that we get as humans, which have multiple genetic alterations, NF2 is very simple. The problem with CRISPR, or the challenge, is we don't yet know how to give CRISPR inside every cell in the body. So we're struggling with the delivery is the issue. So I think once we get the delivery down, which has been very challenging, I think it's going to be a game changer for all of us. But that's still the challenge. Yeah. That's what we're very interested in. And when Elizabeth was showing some of the spinal fluid results, we're also going to be giving the gene therapy directly into the brain. And so we're going to use some of the same techniques that Elizabeth was talking about. Yeah. Because that way we don't have to deliver it through the liver. If you give it into the blood, as you know, it gets filtered by the liver first. And so much of these things it's a problem.
The question on the CAR T therapy, so they've all received just one course, one infusion. Yes or no, or?
The 2 out of those 3 patients that I presented received 2 doses.
2 doses, okay. And so do you reinfuse, or do you infuse all of the production of the first go around of the cells, or do you hold some back for a second?
We hold some back. So we give them about 10 million cells in each dose. And so when you take the cells out, you can make a certain number of doses that you can give to a patient. Anywhere from 4 to 6 is the yield that we usually get. And so one of the modifications that we're making to the trial is to now do multiple dosing about every 4 to 6 weeks. We're hoping to try to redose them as a way of making the T cells persist for longer.
Okay. And so they're still targeting the same 1 or 2 antigens through all of that. Is there concern about the antigens or different antigens starting to express, ongoing mutations, which always seems to be a problem?
Right. We're always worried about that Darwinian pressure, that we can eradicate the subclones of the tumor that express our target antigens. But the idea is, because we also are activating T cells locally within the tumor microenvironment, we're hoping that we can turn on the immune system so that it now starts to recognize other antigens in the tumor, in addition to the 2 that we specifically designed for, and just turn on that local immune response so it starts to recognize other subclones as foreign and starts to attack the tumor.
Okay. All righty. Great.
My question is on funding. How much funding comes from private and from potentially federal money? And with our nation going forward with election tomorrow, are you concerned about funding from the government, or do we continue to get most of your funding from private institutions?
So it's a mix for us. And one of the things I'm proud of is we have an amazing institution. We're the #1 research hospital in America, and by extension the world, there's no question. We have the most industrious system and support. Having said that, we still never have enough money to get done what we do. So the way I think about it is, at least at Mass General, a lot of donations will support the work that's poorly funded federally. So the laboratory scientists are often applying for grants, which is good, and that's the federal government. And then the clinical trial consortiums, like I talked about, the Department of Defense have built up, which are good. It's that place in the middle that's really hard. So for example, you can talk about glioblastoma, I'll tell you about NF2-related schwannomatosis. This work where we're taking Avastin and we're taking the immunotherapy, putting them together, all that work is done from philanthropy between 50 and 100,000 so that you can get that kernel of data. That data I take to the company and I say, this is why you should give us the drug. And so we can build off of that concept. But that money won't come from the federal government because it's not hypothesis based. It's based in what we think is going to help a patient. I mean, there is scientific background, which is why we do it, but it's not the way that they typically fund science.
It's not novel enough for the federal government. Like the NIH likes to fund, to fund really sexy, exciting research, but that's not always, there are things like bevacizumab that you can repurpose for other uses, but that's just not something the federal government is interested in. And then it's also hard to get drug companies interested in glioblastoma because, as I pointed out in the middle, we're a very small market. And so they just don't like to put a lot of their funds. We have a trial going now where the company just went bankrupt. And so they shut down the trial and they're not going to continue it because they can't find a funder. It was a small startup and they can't find a funder, even though they had promising research that it was working to some extent and really deserved to move to the next phase, but there was no funder to take it to that next phase.
So where does that promising research transfer to continue the research?
So I unfortunately, what I know of this company is it's not going anywhere. But what we try to do is use the money we can get to build enough data to say, look, this is something that should move forward. Look at all of this great, research that we found out through consortium studies, the philanthropy to support those smaller studies to say, look, there really is something here that you should support.
Well, to be clear, the two projects you heard tonight, which was just coincidental, are both MGH-funded science that started off in MGH labs funded, not through federal sources. The difference is when you think about Pfizer creating COVID-19 vaccine, or you think about some of these immunotherapy programs for lung cancer, those are company-driven. Neither of these are company-driven studies. These are observations that were, Brian Choi in his lab created this, we call it a construct. It's really like an engineering construct. He proved that it was effective. For us, it was about repurposing an approved drug for a novel indication, and that kind of stuff rarely, if ever, gets funded at the earliest stages. After you've shown a good response, they're happy to give you money, and so the idea is this seed money is what brings us forward. Yeah.
Thank you.
But it's frustrating. I'll tell you just the other thing that's really hard for me as the program director is a lot of our junior people get lured away, my word, to some of the drug companies. And I say that tongue-in-cheek because they're doing very important work too. But one of the things for me is trying to keep all these very active researchers, at Mass General to continue this work. That's not just what the drug companies think they have an indication that can make their return on investment. That's important, but we do something important too, I think.
So there's a lot of promotion around artificial intelligence. And one of the areas that they particularly talk about is drug development and healthcare. And I'm wondering how much of this is hype and how much is, a real potential for some future breakthroughs to develop and test drugs, for example, at a much faster rate, and perhaps provide more of the data that you need to get funding to do some of the clinical trials that you're doing?
So I don't know the answer. I think I feel like I'm in the same position. Sometimes I hear stuff that I think is incredible hype, and sometimes I think there's real promise. I'll tell you one thing that I think has real promise, and that is last year the Nobel Prize in Medicine was about using AI to take a sequence of amino acids, which are the building blocks of proteins, and then based on this incredible database it has, it can predict the folding of the protein. Because proteins, instead of being a chain that's in a row, they have what we call a conformation, where a three-dimensional structure. And why that's important is that 3D structure, which in the old days had to be proven by what we call X-ray crystallography, like when they shoot electrons, X-rays through these proteins. Being able to do this through AI allows the researchers to look where a drug can fit to disrupt the conformation. That's how all of our drugs work. So I think that's real. It's not going to help me, because the amount of money you need to have that access in 2024 is a drug company type of, it's a Pfizer, it's a Genentech, and so forth. 20 years from now, maybe we'll have access, because we know, of course, that these costs keep coming down. So I do think there's going to be some opportunities. I don't know if you agree or disagree, I don't think they're going to hit us immediately. But I think our role is slightly different in the ecosystem. Our role is to work with patients, identify the problems that need to be answered, and then go to the companies where they're doing all this and make sure they give us the right drugs and we set up the study. So I'm okay with me not having access to the AI. What I need to do is to connect the drug companies to the right problems and the right patients. At least that's how I see my role.
No, I think that's well said. I think we're still in the infancy of trying to figure out how AI is going to optimize medicine and drug development, and I think we've got still a little ways to learn.
But a lot of the work you've been doing has been, can you use AI, for example, to look at a tumor under a microscope and to extract information that the human eye can't see? Can you look at under the microscope and learn something about the genetic alterations in that tumor, or why it responded to a drug or didn't respond? And you guys have been doing that. So I do think there's going to be some wins in the next few years, would you?
I think there's some areas of lower hanging fruit where AI can have a more immediate impact than, say, drug development. But yes, looking at MRI scans, pathology, those tumor under the microscope, that has a little bit more early promise of where we could play a role. Also, there's AI can actually look through the medical record, and there are stories where it can pick out early signs of disease before your primary care picks it up, and maybe can give the primary care a nudge that this person is maybe showing signs of depression, and so maybe you should intervene earlier. So there are sort of tools like that where I think it might have a more immediate impact.
What happened to those 3 patients in terms of, you said that one of the things that happened was that the CAR T effect, went away soon, instead of, oh boy, we got, years of this. When it lost some of its efficacy, did the tumors grow back? And did they grow back quickly, slowly?
So 2 out of the 3 tumors grew back within about 3 to 4 months. One of them, it didn't grow back until about 7 or 8 months later. And so, we did see that early impact, but the duration of response is what we really need to optimize. So that's what we're working on. And I think we're doing better this time around. I can't say anything because it's still a little too early to tell, but I'm cautiously optimistic we're doing better this time around.
How do you choose the people to do these trials? I come in with a brain tumor. How do you choose me?
So each trial is written with very strict eligibility criteria to say whether or not you're a good match for whatever that drug is that we're testing. So for the CAR T trial, your tumor has to express the antigens that the T cell is supposed to attack. Because if that tumor doesn't express the target of the T cell, it's not going to work. So that's sort of one big step, is making sure that the tumor makeup matches the target of the drug. And then there's kind of a discussion with the patient and the family. I mean, our trial is pretty involved, and there's a lot that we ask of the patients to participate. And so we have a very serious conversation about kind of, are you strong enough, healthy enough? Do you have good support to participate in the trial? So there are some strict eligibility criteria to make sure we're not causing more harm than good. But we also try to be as open as possible so the patients know what they're getting into, and it's something that they're willing to undertake. I mean, I am so grateful to the patients in this trial because we ask so much of them to participate, and they put up with a lot. And so they're just amazing champions, and they have such courage to participate. It's really kind of keeps me going every day to see this.
Do they stay in the hospital the whole time?
So they do come in, they get admitted for the injection, and then we watch them in the hospital for 7. We're cutting down on the time. That's one of the things we need to do to make it more palatable to patients going forward. And if we're going to do multiple infusions, we're trying to minimize the amount of time that they're in the hospital. So it's a big ask of patients. And so that's why we have to keep tweaking it as we learn to make it a therapy that we can give ideally as an outpatient at some point.
You just explained some of the criteria, and I sort of wonder how far geographically afield, recruit's not a very good word for this, but do you go try to identify candidates?
It's been we had so much interest after the New England Journal article got published. We've set up a central email inbox and had to have a phone line to sort of provide patients with information on what are the eligibility criteria so they could figure out if they're a match. But it is tough to ask somebody who lives, in California or, Hawaii or even Texas to come relocate to Boston for what ends up being, a 3-month plus stay where you have to be here because it is a first-in-human study. So we follow patients very closely for really the first 6 months, meaning weekly visits, then every other week visit, and then monthly visits. And so it's really hard to commute from California or Texas to do that. We're open to anybody who is eligible and is willing to, participate. We don't want to exclude anybody because of geography, but it is a big ask of patients coming from afar.
So that sort of sounds like most come from New England.
Most come from New England, but not everybody.
And can resources in remote areas do some of the initial identification of?
Right. We try to screen people as much as possible ahead of time so people are not traveling to Boston just to find out that they're not eligible. So we do very
thorough.
There
are hospitals who can identify that information.
Right. Or they'll, the patients will send me their records, their MRI scans. I'll look through it and say, okay, yes, you would be a good candidate based on at least the information I can gather from your records or conversations with you. We do try to spare them a trip if it's not necessary or if they're not going to be eligible.
These eligibility criteria, it's important to know, are reviewed by the FDA. So these are not stuff these are discussions we have about what's appropriate safety, because the FDA, their number one mandate is to make sure that what we do is appropriate, right? So these are very long and detailed. How long were you getting your IND and whatnot? So detailed discussions.
And so did you say 51 possible participants?
21 total, yeah.
And how long might that take to identify and handle?
I don't think I think we'll complete accrual probably in the next 12 months, I would anticipate.
That is good. I'm glad to hear that.
So just to continue the discussion about the screening of the patients. So everyone who's diagnosed with a glioblastoma, are they routinely tested for these 2 antigens, or do you only test after you go through all the other screening?
It depends on your institution whether or not you get tested. Most people nowadays will get next generation sequencing, so pretty full sequencing of their tumor. And so it's done as part of the initial testing of the tumor. Not every institution does that. So that does become a bit, if the patient hasn't had that done, that's sort of the first request to see if they can get that testing done to see if they're eligible.
Okay.
Somebody who makes it to us usually comes from a pretty sophisticated hospital. I'm not sure everybody gets complete tumor sequencing, I'll just say.
Thank you.